Okay, and we'll go from current slide. I hope it's working now. All right. Any questions on anything we've done up to now? Okay. We're still in 1.1, and hopefully we will get out of this pretty soon. And we're at example 2, the bottom of page 4. Okay. Now, I can remember saying something right at the end of the last class, and it was concerning this. This is one way you can express a differential equation. M of xy dx plus n of xy dy is equal to 0. Now I remember saying, and when it's written in this form, you can't tell which is the independent variable and which is the dependent variable. So example 2 is going to take care of that for us. It's going to say, if we assume that y is the dependent variable, okay, in the first order ODE, then recall from calculus that the differential dy is defined to be and this is one of those strange little statements, y prime dx, okay? If y is a dependent variable, then dy is y prime dx. Now, if that seems like almost a redundant statement, it sure seems like it to me too, because that's saying that dy dx, if you wrote this not in differential form, is equal to y prime, which is dy dx. Okay, so yeah, you're basically saying it's an identity almost. It's not quite. So therefore, by dividing the differential, and this is something that most mathematicians would cringe at, dividing the differential dx an alternate form of the equation can come up. So here's what we start with. Y minus x dx plus 4x dy is equal to 0. All right. Now what this is a differential equation in differential form. You don't have a derivative in it, you have a differential, dy's and dx's. And this is just like what we have at the very top. Your m of xy down here is y minus x, and your n of xy over there is just simply 4x. No y in it. But it's okay. Okay? Now, to write that in more of a standard derivative form, what you can do is divide everything by dx. Okay? Well, here the dx's go out, and you get y minus x, plus 4x dy dx is equal to 0, because 0 divided by dx is still 0. Or, you could write this way, 4x dy dx plus y is equal to x. Now, I don't know if you've noticed this yet or not, but you will, okay? This is what we call sort of a standard form of a linear differential equation, okay? Notice the coefficient for the dy dx has only x's in it. The term with the y, if it had a coefficient, only had x's in it. And then on the right-hand side, you have all the functions of x. So this is your standard differentiation, a standard expression for a linear form. So you went here from a differential form, no derivatives in it, to a linear form, which does have derivatives, functions of y, and functions of x. Okay? So, any questions on that? Okay. It's just going back and forth between sort of derivative forms and differential forms. So let's go the other way this time. If y'all are through with that, well, I'll let you finish. Both of you through with it? Okay. Let's go the other way with it on this one. Here is a 6xy dy dx plus x squared plus y squared is equal to 0. Now, time out for just a moment. That is that a linear differential equation? No way, okay? On several counts. One count, here you have a y factor and a derivative of y in the same term. That would throw it out. Then you have the y squared here. That would throw it out, okay? You might be really tempted to divide every term by y. This would be okay then. That would be okay then, but then your other term would have a x squared over y. That would not be okay. So no way you can make that a linear. But it's okay. I mean, it doesn't have to be linear. Okay? What if we wanted to write this in differential form? What would you do with that? How would you do that? Yeah, okay. Most mathematicians cringe when you say that, but that's exactly right. 6xy dy plus x squared plus y squared dx is equal to 0. Okay? Now, later we'll identify, now you could swap the terms on those if you wanted to, but what's the purpose? Later we'll call this, it sort of gripes me sometimes, they use the same terms for different things. Later we'll call this a homogeneous differential equation because this term has power 2, that has power 2, that has power 2. They all have the same power in every term. And then those are sort of special equations in some senses too. Now what they did is turn around just like I thought they were going to. X squared plus y squared dx. So traditionally we put the dx's first. Plus 6xy dy equals 0. Nothing any better or worse about that. All right. Now, when you have an equation like this, okay, that you got equals 0 on the other side, okay, later still they're going to call this a homogeneous differential equation, not because of the same reason as before, but because the right-hand side is 0. So they use the same word for two different meanings, but you just need to know the context. This happens to fit both meanings, but that's beside the point. But you can, if you can take an equation, any old equation, and write it in a general form such as this, f of some x, some y, and then some derivatives of y, y prime, y double prime, y triple prime, dot, 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 up to and including y to the n minus 1 equals 0. If you can write an equation like this, and I'll put more terms than they did in the book, where f is a real valued continuous function, this is said to be a normal form. Okay, don't sweat, this is a r in front of that, it just sort of ran together, of equation 4, which is way back, well, where is it? Oh, there it is. I'm sorry. That is itself. Okay. Wait, I misstated something here. This is not n minus 1, this is n. I was thinking that looked strange. As the nth derivative, okay, is equal to 0, where f is a real value function of n plus 2 variables. Your derivatives alone are 1, 2, 3, 4, 5, 6, up to n terms here. Those are all different variables, okay? Then your x and your y are 2 more, so that's where they get the n plus 2 terms, okay? For both practical and theoretical reasons, we also make the assumption hereafter that it is possible to solve an ordinary differential equation in this form uniquely for the highest derivative, y to the n, whatever that is, and write it, and I'm sorry, this is not the normal form. My eyes jumped down the page. Oh, I see what I did. I went from 4 to 5 and combined them together. Sorry about that. This is aggravating. Okay. That is a way to express it. If you took out the dny dx squared, dny dx, not squared, to the n, and then set that equal to some other function, little f. Now this is a lot like we did in calculus. When we did fundamental theorem of calculus, we did the capital F to be the derivative form and the little f the antiderivative form, or vice versa. That's not what these capital and little f's are. Kind of like that in that it's one derivative less, but so in many ways it is like that. So this little f is some function of x, y, y prime, y double prime, y triple prime, dot, 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 up to y to the n minus 1. That's where my n minus 1 came from. And you don't have to equal 0 there because you have your equal sign over here. Okay. Okay. Now, this is called the normal form of this, the normal form of that differential equation. So there are some times when we'll write dy dx, this is just first order, is equal to some function of x and y, and other times when we'll, and other things like this, d2y dx squared is equal to some function of x, y, and y prime. Okay? This would then be a normal form, whereas the other way to express this one would be capital F of x, y with equal, I'm sorry, don't have quite enough terms in that. Capital F of x, y, y prime is equal to 0. So these two are equivalent forms. This has the derivative outside, this has the derivative inside. This would be equivalent to capital F of x, y, y prime, and y double prime is equal to 0. So you just move the second derivative back into the fold and leaving a 0 on the other side. Those are different functions, capital F and little f, but of course they have to be somewhat related. All right. That being said, and frankly these are terms, we'll come back and use them a little bit, but this is the most you'll ever see of them, pretty much, okay? And it sort of baffles me why they spend so much time dealing with them, but I guess they do. All right, so let's do 3a. For x dy dx plus y equal x, what would be the normal form of that equation? Now, that's not your capital F form. That's just another form. The normal form always starts with basically a naked highest order derivative, which would be your dy dx. So how would you get this into a normal form? Anybody? Okay. Okay, you could do that. Let's do that. Minus y. So now you have 4x dy dx is equal to x minus y. Okay, that's fine to do. Nothing wrong with that. Divide by 4x. Okay, so this would then be dy dx. This is how a normal form starts, except it's not dy dy, it's dy dx. Okay, is equal to 1 over 4 minus 1/4 y over x. Okay, which you could have written 1/4 1 minus y over x, or any other way such as that. That would be the normal form for that equation. Okay, here's another way they did it. Let's multiply this equation by x over x, and this would be x minus y over 4x. So there's another way to write it. None of these are any better than the others, and frankly, I don't know why they're spending this much time doing it, but these are all correct things. Now, if you've got your book, watch out number B. There's no way that it's correct. And I don't know what is supposed to be the correct form for it. But anyway, let me write down what number B says, and then we'll try to figure out, well, there's no way to tell. So here's how it starts. Y double prime minus y prime plus 6 is equal to 0. Okay? Write that in its normal form. Not that hard.
Take everything but y double prime, put it on the other side.
Yeah, or take everything else and put it on the other side. Yeah. Add y prime and subtract 6 from both sides. Okay, you get y double prime is equal to, because both of those go to 0, y prime minus 6. Okay? Now, looking at what they said the answer was in the book, they said 6y. And I went, what? How can you possibly get that? You can't. Either that should have been a 6y here, then this would have been your answer. Or if that was indeed the problem, then it's a 6 without the y. Now, I don't know which they intended. It really doesn't matter. It's just solving and getting a normal form where you put your maximum derivative by itself on one side, everything else on the other side. I don't know which they meant. If this would have been the case, you would have had to have a y here and here, okay? but they didn't have a y there and there. All right. Now, oh, yeah, I hadn't realized we hadn't talked about classification by linearity yet. Thought we had. Sorry about that. Are we really that far back?
We really were. Last thing we wrote was the thing right above example 2.
Right above example 2. Yep, that's what I had. Okay. Wow. I guess we just got such a... Oh, yeah, we had to go over syllabus. We had to go over... Yeah, we did. This is our first full class, and we got late to start on that. All right. So let's now talk about classification by linearity. We've been going so long, I thought we'd already done this. Okay? So let's start with a clean sheet here, since this is a new form of classification. An nth order ordinary differential equation, as in number 4, up there, that capital F form, okay, is said to be linear okay, if that capital F, okay, is linear in every form of y. Y's, y prime, y double prime, y triple prime, dot, 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 up to y sub n prime, okay, the nth prime of y, okay. If every one of those is only in a linear form, okay. Here's another way you can express that. That equation could be written as a sub n as a function of x, dny dx to the nth. That n up there is supposed to be raised, and somehow it fell down. Okay. I can't get my pen to come back. There we go. Okay. Plus a sub n minus 1 of x d n minus 1 y dx plus a sub n minus 2 as a function of x d to the n minus 2 y dx to the n minus, oops, this is n minus 1 down here, and this is n minus 2 here. Now they don't usually put parentheses around them, but I just get sort of freaky not doing it, but I'm trying not to, okay? Plus, and we'll just put a dot, dot, dots there until you get finally to your last term, a sub 1, next to the last term, of x dy dx, that's the first derivative, so that has a match, plus a sub 0 of x is equal to 0. No, I'm sorry, it's equal to g of x. All right. Now, let me explain to you what this means, maybe a little bit about what it doesn't mean. Your coefficients here don't have to be just numerical coefficients. They can be functions, but they can only be functions of x. Okay? And they can be cubed, squared, 14th power, 3/2 power, nonlinear things like sines or exponentials or anything else. The x's can be. The y's and the derivatives of y's can only be, whoops, I missed one. That's a sub 0 of x times y. Okay, I left off that y. Yeah. Okay? These terms of y can only be to the first power. Every derivative of y to the first power and y itself to the first power. There also can't be any cross. You can't have a y prime, y triple prime in the same term, because then it would be a y to the second power. So, and you can have a y to the 3 half power. You can have a y to the 3 half, 3 halves derivative. You can't have y to the 3 halves power. It can only be to the first power. Every derivative of y and y itself only to the first power. The coefficients can be any kind of functions of x. The thing on the right-hand side, any kind of function of x. No y's over here, okay? If there's y over here, it's not a linear function. Okay. Yes. There are some cases it could be, but generally it would not be. You write all the y's on the left-hand side. Every term has a y or derivative of y over here. On the right-hand side, x's only. Okay. And these are called linear ordinary differential equations. Ordinary because they're not partials. Linear because your y's and your derivatives of y are always to the first power. No multiplying or dividing of any of those. Okay. They can't be to fractional powers. They can't be to negative powers. They have to be to the first power only. Okay. So, two characteristic properties. The dependent variable y and all its derivatives are of first degree only. The power of each term involving y is 1. The coefficients, a sub 0, a sub 1, a sub 2, up to a sub n, and your of the y and y prime all that depend on most the independent variable x. They could be constants, but they can't depend on anything other than x. And they can be all kinds of nonlinear forms of x. That doesn't matter, because your y's can't be. A nonlinear ordinary differential equation is simply one that's not linear. So this is a binary thing. It's either linear or it's not. Okay? Nonlinear functions of the dependent variable or its derivatives, such as sine y, e to the y, cannot appear in a linear equation. Okay? I think we could probably do this one okay, but let me erase just in case we need more room. All right to erase? Okay. Here are some equations. Y minus x dx plus 4x dy is equal to 0. Now, can you just look at that and tell me whether that's linear or nonlinear? Say again, nonlinear? Why is that?
First term, y minus x, is that dx or dy?
It's a dy. I mean dx. The first one's a dx, the second one's a dy. Okay.
I'll change my mind.
Okay. And it may be. But I can't just look at it and tell without actually doing some writing to it. So what I'm going to do is divide everything by dx. Okay? So let's rewrite this as 4x dy dx, okay, plus y minus x equals 0. Sure enough, you're right. Your changed opinion was absolutely correct. The only coefficient here has only x's in it. Could be any form of x, it doesn't matter. This one here, and this is just to the first power. The y's to the first power, its coefficient is 1, which is perfectly fine. And then you could move this to the other side, 4x dy dx plus y is equal to x. There it is. The right-hand side is only functions of x. The y's and derivatives of y is only to the first power, and the coefficients here could have x's in them or constants. So yeah, that's a linear function. Okay? How about this one? y double prime minus 2y plus y. I think here's another error, but I can't tell, equals 0. Now, if that indeed is how they meant it, then you can rewrite this as y double prime minus y equals 0, and sure enough, that's linear. You can be missing a y term, a derivative of a y term. That's okay. It's still linear. Okay? However, I have a feeling they meant that to be a y prime. If that's a y prime, it's still linear. Okay? Whichever way it is, those are both linear forms. Okay? How about this one? X cubed d3y dx cubed plus x dy dx minus 5y is equal to e to the x. Okay? Linear or nonlinear? It is linear. Doesn't matter about the coefficient functions, x here, minus 5 here. Doesn't matter about the right-hand function, that can be anything. Only x is there. It's the y terms that matter. This is to the first power, that's to the first power, that's to the first power. So yeah, you're fine. Does it matter you're missing a second derivative? No. Its coefficient is 0, which is linear. Okay, so yeah, that is a linear function as well. Okay, how about this one? How about that? Is that a linear function? Yeah, you got y's and your y prime in the same term, and I can't think of any way to undo that. If that had been just a minus y prime, then you could divide by y. However, then your term out here would have been e to the x divided by y, and that would have been an exponent of 1. That would have been an exponent of minus 1. So no, not linear. Okay? Sometimes you can do some manipulation with it and make them linear. This one you cannot. Okay? How about this one? d2y dx squared plus sine x, no, sine y equals 0. No, because this is not a linear function of y. This is a nonlinear function of y. Sine y is definitely not linear. How about if it had been sine x? Yeah, this would have been to the first power. That you can move to the other side, functions of x alone. That would have been linear. How about this one? d4y dx to the fourth plus y squared equals 0. No, because the y squared is not linear. That's squared. Okay? So no. The first one's perfectly fine. It doesn't matter which derivative it is, as long as it's not multiplied by another derivative or y itself or raised to a power that the total degree of your y's are, not the derivative of y, but your degrees. Okay. Now, here comes another definition. And if it sounds like it's sort of familiar, it seems like we've done it before, but here's what it is. Any function, they're going to call this phi, as in phi, phi, pho, thumb, okay? Phi defined on some interval I and possessing at least n derivatives that are continuous on I, okay. Goodness gracious. I'm losing my voice. I don't know why. Maybe because I've been talking all day. At least n derivatives that are continuous on that same interval, which when substituted into an nth order ordinary differential equation, ODE, reduces the equation okay, is said to be a solution of the equation on the interval. Goodness gracious. That's ugly writing. I'm sorry. Screen keeps disappearing on me. So in other words, a solution for an nth order ordinary differential equation is a function phi that possesses at least n derivatives and for which, going back to our other form of writing it, f of x, phi of x, phi prime of x, phi double prime of x, phi triple prime of x, keep on going, up till you get to the nth derivative of x, okay, is equal to 0. Okay, when you plug those in and all the derivatives into that function form that you had. Now you got functions and functions. This is a function. That's your solution function for the differential equation. And these are the individual solutions to the individual. This is the differential equation itself, and these are the solution functions to it. And when you plug those in, you're always going to get the identical 0. Then that's called to be a solution. And that's for all x's in I. Okay, in the interval. We say that phi, the function phi, satisfies the differential equation on the interval I. Okay. Now it says, for our purposes, we shall also assume that the solution phi is a real valued function. Okay, what basically that's saying is we're not allowing complex solutions and roots. We're going to have them real valued functions. Okay, real valued solutions. Okay. Now, that doesn't mean that complex forms don't pop up, but we deal with them until we get rid of them. Okay, and we'll see that a little bit later. That's going to be at another junction, well down the road. Okay? All right. Now, another statement here. You cannot think of a solution of an ordinary differential equation without also simultaneously thinking interval. Okay, of the interval for that differential equation. Goodness, I can hardly read that. Goodness gracious, that's terrible. That's the interval. Yeah, I can see it now. Let me erase this a little bit. The interval. So you always have to do that. Sometimes that's called the interval of definition. Okay. Interval of existence. Okay. Interval of validity. Or the domain of the solution. Now, it almost bugs me a little bit but not enough to really do much about it, to not say this every time. But after a while, you just sort of assume that you know what that interval is. We won't always write it down and say it, this is it, but a lot of time we will. And because there are sometimes it's really blatantly obvious this cannot be a solution, okay? And sometimes I'll remember to say that, and sometimes I won't, but always you need to really think it. So. It can be an open interval. Okay, now I don't know if you recall what we mean by an open interval. That's one that does not have a fixed endpoint. Okay, open. You can have one endpoint open and one closed and the other open, but an open interval, neither one of them generally are fixed. Now, when you see an interval listed as minus infinity to infinity, that's open. There is no end value to it, okay? So those always have parentheses around them, okay?
Question.
What's that?
When you got the so-called half open interval,
Right.
does this apply?
Okay, in other words, something like this. Yeah. Yeah. I was going to say the interval can be any combination of them. So that is an acceptable interval. That wouldn't be an open or closed. That's, like you said, half open, half closed. Minus infinity to positive infinity would be open. -7 to 8 with a parenthesis on there 7 would be open. So it really doesn't matter. Like I'm saying, sometimes I'll forget to say what that interval is, even though it may be pretty obvious that the 8 could not be included, but I'll forget to say that and say the interval. But, for a little bit, we will try to focus on that, okay? So like example 5. I know last time I ran over, and then I take my watch downstairs.
So like 3:30.
3:30, and we go to 3:45. It sort of bugged me. I don't know what I did with my watch. Usually I leave it in the classroom, but I must have.
Under that sheet right
There
there.
it is. You got it. Thank you so much. Okay, yeah. Got it. All right. So let's go to example 5. Verify that the indicated function is a solution of a given differential equation on some interval, and they say this one's from minus infinity to infinity. Okay? Here's the differential equation. dy dx is equal to xy to the 1/2. Okay. Y is equal to 1/16 x to the 4th. Okay. Now, I don't know if you remember me harping on this before, at least mentioning it before. For what we're going to do in this chapter, mostly, chapter 1, we're not going to solve, I want to say, hardly any differential equations, period. What we're going to do is verify they are solutions. And that's what they're asking us to do here. They give us, they say, verify. The left-hand side is a differential equation. Okay? Okay? Left of the semicolon, that's a differential equation. dy dx equals xy to the 1/2. The right-hand side is a potential solution to that differential equation. What we're asked to do here is verify that solution is a solution for this differential equation, and we need to justify that it is a solution for all real numbers, negative infinity to positive infinity. Okay? How would you tell? How would you verify? Take a derivative. Very good. Y prime is equal to 1/4 x cubed. Perfect. Okay. Now, we got one other thing we've got to do. We need to figure out what y to the 1/2 is. Because this takes care of this side, but we still need to figure out what goes in here. So what is y to the 1/2? If y is 1/16 x to the 4th, what is y to the 1/2? Square root of that would be the square root of 1, or let me just write it this way, x to the 4th over 16. And what would that be? X squared over 4. Perfect. Now let's plug and chug and see if it indeed works. Your y prime, which is dy dx, is 1/4 x cubed. Is that equal to, we don't know this yet, x times x squared over 4? Well, guess what? X times x squared is x cubed over 4, which is the same thing as 1/4 x cubed, right? So we have verified it. Now, what makes that good from minus infinity to infinity? Okay? What's that?
No zeros in the denominator.
No zeros in the denominator, no negatives in square roots, no negative logs, or anything else such as that is not allowed, so we're perfectly fine. The fact that y is to the square root here, it just says y can't be negative. Okay? Well, guess what? Y can't be negative. Because we're assuming, remember, that the x's are all real value functions. So if that's the case, whatever value x has, when you raise it to the fourth power, it's always positive, negative, negative. It could be 0, but you can take the square root of 0 with no problem. So yes, this is good everywhere. Okay? There are, like you said, no places that get you into trouble. Okay? That's not what you said, but it's what you were describing. How about this one? Let me clean to a new screen. Is that okay? Y'all got it? Okay. Just in case this takes longer than I planned for it to. Y double prime minus 2y prime plus y. There's your differential equation. Here is their proposed solution. I'm sorry, y is equal to xe to the x. All right. What are you going to have to do to verify that that is a solution to that differential equation?
Get y prime.
Okay, let's take a derivative. Y prime is equal to x. Okay, say again.
So, e to the x.
Okay, e to the x, how about that? Did you say something else? I didn't know.
Is it e to the x
Plus
x e to the x?
x e to the x. Perfect, absolutely. Because it's a product rule situation, right?
Yes.
The derivative of the first times the second, derivative of x is 1 times e to the x. That gives you e to the x plus the first times derivative of the second, x times derivative of e to the x is e to the x. So yes, that's correct. But you also need to y double prime, and that would be equal to
X e to the x.
okay, you started with x e to the x. Yeah, that's fine. X e to the x plus
e to the x.
e to the x plus e to the x, which you could write as x e to the x plus 2 e to the x, right? Okay? Another way you could write it, that not that this is any better, but you could have pulled out e to the x times x plus 2. You could do that, but you don't have to. I actually like this middle form best. Okay? So let's plug and chug. Okay? Your y double prime is x e to the x plus 2 e to the x minus 2 times your y prime is e to the x plus x e to the x plus y, and y is x e to the x. The question is that equal to 0? Well, this is x e to the x plus 2 e to the x minus 2 e to the x minus 2x e to the x plus x e to the x. Is that equal to 0? Well, looking at this, 2e to the x minus 2e to the x, sure enough, that's equal to 0. And here you have minus 2x e to the x and plus an x e to the x plus e, so that's plus 2x e to the x. So sure enough, all those add to be 0. Okay? And x e to the x is defined everywhere. Product of two functions that's defined everywhere is defined everywhere. And its derivatives, you can take as many as you want to till the cows come home. They're defined everywhere. Okay? So sure enough, that is a solution on all real numbers for x. The interval negative infinity to infinity. Okay. Now, if you think about a function such as this, and we just said it was fine for all real numbers x, okay, including x equals 0. Well, x equals 0, what's your y? 0. Okay, anytime that y is equal to 0 is a solution, it's called your trivial solution. If y is equal to 0, y prime is equal to 0, y double prime is equal to 0, y it's all the way. So that's called a trivial solution. And if that fits the case, let's see how to express this. Note too that each differential equation in example 5, and I've already erased the first one, but that was y is equal to 1/16 x to the 4th. When x equals 0, y was equal to 0 there. So in both of those, the solution for the differential equation is identically 0 on the interval I. That's said to be a trivial solution. Okay. I think this may be the last thing we have time for. They're mentioned here a solution curve. The graph of a solution phi of an ordinary differential equation is called a solution curve. Now that says of a solution. We're going to find out that sometimes you have what they call a family of solutions. Now any one of those solutions has a solution curve. Sometimes a family will have sometimes an infinite number of curves. Usually we represent by just a few, but so when you do have a graph of them, it's called a solution curve. If you had y is equal to 1 over x was a solution for a differential equation, obviously x cannot equal 0, because that would then be one of those cases not going to happen, because you can't ever divide by 0. Well, its graph could then look like this. That's for positive x's, that's for negative x's. Okay? Now, obviously, x cannot equal to 0. So the interval of solution is either going to be something over here or something over there. You cannot go across here because x cannot equal 0. So it could be from negative infinity to 0 with 0 being open, or from 0 to positive infinity, with both of those being open, of course. Or it could be from negative 7 to negative 3. That would be fine. or 0 open to 15. That would be fine. Or 1 to positive infinity. You could have any of those, but you cannot have an interval of solution that crosses a place where it's not defined. Okay. So that's this other thing dealing with, you can't talk about a solution without also talking about its interval. If that's a solution, it's going to be either this side or that side or some fraction, but it cannot ever cross. Okay? So, I think we're out of time now. All right, we'll begin next time at, I swear I had up here, there, wound up in there. Okay, we'll begin next time with example 6. I'm sorry we didn't get any further than we did this time. Had a late start, mostly because of the power outage and the repercussions there. Whoa, still got several pages to go. Homework exercises in 1.1, be any of the odds in the back of the book, okay, any of the odds that are in the back of the book 1 through 7. Okay. Think you could do 9 if that's in the back of the book. Believe you can do 11 or 13. If that gets to be a little hairy, we'll wait and do some more first. I think we'll hold off on the rest of it. All right. All right. Okay. Good deal. So that'll pretty much cover it. All right. Any questions?
Well, I just hope my book got
Yeah.
addressed today.
What's that?
I just hope the book that I ordered.
Oh, will come in. Well, we're going slowly enough. You're not going to miss a lot.